Okay, so let us quickly start the tutorial for week 7. So as you know that this tutorial is mostly based on the laws of first law of thermodynamics and the different processes, thermodynamic processes like isothermal, adiabatic, isobaric, isochoric, etc. And work done, heat absorbed, etc. things you have to calculate in these problems. So basically mostly based on the chapter of first law of thermodynamics. Okay, so let us start with the problems. First, what we'll do is that we'll first finish the previous problems, which are some parts which are similar to the current week's problem, and after we finish that, then we'll solve the extra problems which are not similar to these like the current week's problem, which are not similar to the previous problems, which that we'll also cover. Okay, so let us start then one by one. Yep. Right, so let me choose my pen. So first question is that, so this is, first of all, this is week 7 tutorial. Okay, so first question is that the 1 gram mole of a perfect gas expands isothermally to 4 times its initial volume at 27 degrees centigrade. Then calculate quantity of heat which is extracted from this work. Okay, so you have information that you have an ideal gas or perfect gas and the quantity is 1 gram mole, or in other terms 1 mole basically. And it expands isothermally. That means it is an isothermal process where the temperature remains constant throughout the process, right? And it expands to 4 times of its initial volume, and the temperature constant average is also mentioned, which is 27 degrees centigrade. That is, you know till now that this is the same as 300 Kelvin basically. Then calculate the quantity of heat which is extracted for this work. Okay, so we have to calculate what is the heat absorbed for this process of isothermal volume expansion. We have to calculate the heat absorbed for this work. Okay, so let me choose a blank page and start solve it. So this, what we are discussing right now is previous problem set. This is not the current week's assignment problem, but you will see that even I think the first question is just same as the first question of the current assignment, or as far as I can remember, but we'll come to that later on also. So the current assignment will also be discussed and solved, right? So let us now consider on this. So the first problem is saying that it is an isothermal process. Isothermal, as I said, it means that throughout the process the temperature is constant, T is equal to constant, and that constant value they have mentioned, which is 27 degrees centigrade. That is 27 plus 273 is equal to 300 Kelvin, right? And the quantity of the gas is just 1 second. Yeah, so the quantity of the gas is 1 gram mole. So this is N equal to 1 gram mole or 1 mole basically. And let's say the initial volume we take as V1, which is equal to V, let's say. And the final volume they have mentioned it is expanded into 4 times of its initial volume. That means if we consider V1 to be V, then V2 will be 4 times V, which is 4V, right? This is initial. This is final. Okay, and we have to calculate what is the work done, or in other terms, what is the heat extracted from this work done. So there is a this terminology you have to understand, that because we are talking about isothermal process, and according to the first law of thermodynamics, you know the rule that dq is equal to du plus dw. So this dq is the heat absorbed or extracted, depends on the process that we are talking about. Du is the change in internal energy U of the system in this process, internal energy U, and dW is the work done. It can be work done by the system or on the system, and depending on that whether it is work done on the system or by the system, that depends on the process we are talking about, and that will decide the sign of TW. So I will not go into the details of it because this is already discussed. This is the first law of thermodynamics. I will only mention what is useful to this problem. Okay, so here you know that you have been asked to calculate the heat that is being exchanged in this process, but it is also mentioned that calculate the heat that is required here and that is extracted from the work done. So what they mean is that for an isothermal process, you know the temperature is constant. Isothermal means temperature is constant at a particular value, and that means the change in temperature dt will be 0. And if dt is 0, obviously du will also be 0. So this is a given fact. So this you have to remember that this internal energy, this is a state function. This depends the state the system is in, and it is a function of temperature. So if the temperature is not changing or temperature is constant, then the internal energy will also not change. So this is the rule that if you are taking an isothermal process where the temperature is constant at T is equal to at some T, and so dt equal to 0, that means the internal energy U will also be constant. So this is given that if dt equal to 0, then du will also be 0. So for an isothermal process, your change in internal energy will be 0. What that gives you is that if your du becomes 0 for an isothermal process, that if this is 0 for isothermal process, then that takes you to this first law of thermodynamics being modified into dq equal to dw simply. So for isothermal process, your heat that is being exchanged is the same value as the work done. Okay, so for isothermal process, because there is no change in internal energy is unchanged, so the heat exchanged, either absorbed or extracted, heat exchange is equal to work done. So it does not matter whether you calculate the heat exchanged or the work done in this problem, you will get your answer. Okay, so we will calculate the work done here because that is the same as the heat, right? So in this case, in this isothermal process of volume expansion, the work done is equal to W. You know that the work done thermodynamically is basically PdV, and you have to multiply from initial integrate from initial volume to final volume. So V1 to V2. Now this part is simple. So you know your V1 is V, let's say, and your V2 is 4 times V, so it is 4V. But what you don't know is that you have no information about pressure. So you have to get pressure in units, in terms of V here. How do you do that? So you know that the problem says it is a perfect gas. It is a perfect gas means it is an ideal gas. So ideal and perfect, they are different terminologies of the same thing. So you know that the gas equation for ideal gas is PV is equal to nRT. This is for n moles. But for 1 mole, when there is n equal to 1 mole, so simple equation will be PV equal to RT, pressure into volume equal to universal gas constant into temperature. So from here you can convert your P in terms of RT by V, right? So now this expression has RT and V. So this you substitute here, substitute back here. So what you get is that this is RT by V dV from V to 4V. Okay, and you know that R is universal gas constant, so it is obviously constant coming outside the integral. And similarly, because it is an isothermal process, so T is also constant, it will also not be integrated, so outside the integration. And then it is simply dV by V, and it is from V1 to V2. We'll put the values of V1 to V2 at the very final end. So let us not write down for now. Let us keep them as V1 and V2, initial and final volume. So if you integrate this, you know this will be ln V, and from V1 to V2 it will be equal to RT ln of V2 by V1, right? And you know that the ratio of the final volume to initial volume is 4 because it is expanded into 4 times of the initial volume. So this is simply RT ln 4. So just take your calculator and put the values of the different quantities, where R is 8.314 in joule per mole Kelvin, which is the SI unit in this case. T is the temperature which is given in the problem as 300 Kelvin, and ln 4 value you can calculate from the calculator, and you will get a value of 3.46 kilojoule. So this I have already calculated. You can take your calculator and put the values and you will get this value. So this is the work done. This is W, work done in this process, but because this is an isothermal process, so Q, the heat that is, so because it is expanded, so we understand that heat must have been absorbed, because by absorbing heat it will expand into a higher volume, right? So we'll write heat absorbed equal to Q. It is same as the work done W, and so the heat absorbed will be 3.46 kilojoule, because there is no change of the internal energy of the system. Since the temperature is unchanged, so internal energy will also not change. So this is your answer, and this is option number C that I have marked earlier. So we'll go back and find out whether it is number C or not. So yeah, 3.46, option number C, this is the correct answer. So question 1 is done. So let us move on to question 2. It is saying that for silver, the molar specific heat at constant pressure in the range of 550 Kelvin to 100 Kelvin is given by Cp equal to some function of T. It is expressed in Cp, where T is the absolute temperature. Now, if 2 moles of silver is heated from 50 Kelvin to 100 Kelvin, then calculate the heat required in the process. First of all, you have to calculate the heat, Q. Heat required in the process of what? In the process of heating up a silver of 2 moles. So here N equal to 2 mole of silver from a initial temperature of T1 equal to 50 Kelvin to a final temperature of T2 to 100 Kelvin. So it is heated up from T1 to T2, and in this process you have to know what is the heat that is absorbed for this heating up. Okay, and the other information you have in this question is that the molar specific heat, that means at constant pressure C, so Cp, so at constant pressure this is the specific heat per mole. Okay, so let us go back and solve this in blank. So first of all, let me write down the information we have now. So this element is silver, okay, and the number of moles is 2, N equal to 2 mole. And you have the information that the specific heat at constant pressure, this is per mole, so this is molar specific heat. You have to remember that, because depending on that the calculation might have been different sometimes, whether it is molar or this is just molecular, but most of the time standardly people use the molar specific heat value only. So in the question also it is mentioned that this is molar. So this is for 1 mole. This Cpt as a function of T, 0.076 T minus 0.00026 T squared minus 0.15 calorie per Kelvin, right? So now what is your Cpt? So you have to calculate Q, right? What is the heat absorbed in this case? Now we can use a straightforward formula, and I'll explain why this formula is being used. First of all, you know that the dq will be like N times Cp times dt, where Cp is the molar specific heat, N is the number of moles. Okay. This is molar specific heat at constant pressure, and this is the change in temperature, and dq is the change in heat, or basically the heat that is needed for this dt temperature change, or the heat needed for temperature change of dt. Now why this formula is simply saying that because you know the specific heat is nothing but a ratio of dq by dt basically. So if this is molar specific heat, then this is per mole, or otherwise for now just forget about the quantity or quantization, just think it like this is the ratio of heat per temperature. Or in simple words, specific heat is the measure of how much heat you would require for a certain unit temperature change. That means if your dt is equal to 1 or your unit or your temperature change is unity, so simply Cp will be like dq, or Cp is the measure of how much heat is required for unit temperature change. So if you are increasing your temperature by unit or 1 Kelvin, then dq is the heat absorbed in the process, and if you are decreasing the heat by temperature by 1 Kelvin, then obviously you are dumping down the heat, so then you are giving out the heat by that amount, and that will be reflected in the value of Cp. And obviously if this is a molar specific heat, then this means that the quantity that you are talking about is obviously all the time for 1 mole quantity, 1 mole of the system. So if you have to calculate the net heat, then you have to multiply by the total number of moles that your system has actually. So like in our question, this is not for 1 mole, but in the question they are talking about 2 moles of silver. So then you have to specify a multiplicative factor of n, where n is 2 in this case. Otherwise, if it is just for 1 mole, then simple Cp dt will do. But if there are more than 1 moles, then you have to multiply that mole number to get the total heat out of the system, total heat that is required by the system for the temperature change of dt, right? So this is the idea. Now because you have to calculate the net heat, so q is just simply integration of dq, and this is simply n Cp dt. And since the integrand here is t, so the temperature is now changing from T1 to T2, you know, so integral limits will be T1 to T2, right? And n is constant, so it is coming outside the integral, and rest of the terms, because T2 they have mentioned in the question, it is a function of t only, so that will be integrated out inside the integral. So this is this 0.00026 t squared minus 0.15 dt. Now your number of moles is 2, so put n as 2 and then just simply integrate it out. So 0.076 t squared by 2 minus 0.00026 t cube by 3 minus 0.15 t, and this is integrated out from T1 to T2 limit, right? So now you substitute the values very carefully. The first one is 0.076 by 2, then 100 square. So now this is the time that what is our T1 and T2. So you are changing your temperature from 50 Kelvin to 100 Kelvin. So initial temperature T1 is 50 and final temperature T2 is 100. So you use the values mentioned in the question, and your limit, your upper limit and lower limit of the integral, you substitute it in the expression. So this is 100 square minus 50 squared minus 0.00026 by 3, then 100 cube minus 50 cube minus 0.15 into t is simply 100 minus 50. So there you get your final answer as 403.3 calories. So this is coming in calorie, remember, because in the question they mentioned that your Cp, the expression of Cp was in calorie per Kelvin, right? So if you multiply your calorie per Kelvin, this is also per mole. So basically they are not mentioning, but this is basically because it is molar specific heat that by default tells you that this is calorie per mole Kelvin. So this is not in joule per mole Kelvin units. So because this is in calories, so whenever you multiply this by temperature, so Kelvin unit will get cancelled out, and you also multiply by number of moles. So mole will also get cancelled out, and the final result you get for the heat will be in calorie unit. So unit wise you are also correct. This is 403.3 calorie is the answer. So let us go back and mark the question. Yeah, so option number B is what we have opted, and this is the correct answer. So question 2 is also done. Now question number 3. Let us read that. It is saying that an ideal gas of volume 1 liter and pressure of 8 atmosphere undergoes an adiabatic expansion until the pressure drops to 1 atmosphere. Assuming Cp by Cv equal to gamma equal to 1.5, then calculate the work done in joules during that expansion. First of all, what are the information? That you have an ideal gas. The volume is 1 liter and pressure is 8 atmosphere before the adiabatic expansion process. So this is the initial volume V1, 1 liter, and this is the initial pressure P1 of 8 atmosphere. Then the process this system is going through is an adiabatic expansion. So it is an adiabatic process and the volume is expanding. So this is expansion. Final volume is not mentioned, but the final pressure has been dropped to 1 atmosphere. P2 is 1 atmosphere. P2 not mentioned directly in the problem, but obviously because you see that the pressure has dropped from 8 to 1 and this is an expansion process, so basically the pressure will drop and the volume will expand. So obviously V2 will be greater than V1, but they have not directly mentioned the value to us. But there are other informations, like you have Cp by Cv specific heat ratio gamma is mentioned as 1.5, and you have to calculate what is the work done. So W equal to what? This is what you have to calculate. Okay, and it should be in joules unit. So let us start solving this problem then. So question number 3. So your process is an adiabatic expansion, right? Adiabatic expansion. Adiabatic means no heat exchange allowed. That means the system can neither absorb heat from its surrounding, neither it can dump heat into its surrounding. So the system is absolutely isolated in terms of it cannot exchange any heat with its surrounding, but work done is allowed. Okay, so your dq will be 0. That heat exchange or the change of heat dq equal to 0 for an adiabatic process. And this is an expansion, so your initial pressure P1 is equal to 8 atmosphere. This is higher, and the initial volume is mentioned as 1 liter. And the final, that means after the expansion, that the values are, the pressure has dropped P2 to 1 atmosphere, and the volume we consider the final volume as V2, but V2 not mentioned. Okay, so this is not mentioned in the question. And the specific heat ratio gamma is taken as 1.5. This is Cp by Cv. Now one thing is very simple that you have to remember, that because this is an adiabatic process and there is a certain rule or certain formula you use for adiabatic processes, the relation between P and V is basically PV to the power gamma is equal to constant. Just as you have the Boyle's law as PV is equal to constant, or the Charles law as V by T equal to constant, here also adiabatic process where the heat exchange is restricted, that means you probably understand, or later on you will also see that if it is an adiabatic process and the enthalpy will also not changing, so it is also an isenthalpic process. Just like when you have an isothermal process, so your internal energy also does not change, so that makes your du equal to 0. Similarly, adiabatic process is also an isenthalpic process, and in that case the formula or the relation between P and V that is followed is PV to the power gamma equal to constant, and let us name this constant as A. Okay, and this gamma is the gamma of the specific heat ratio Cp by Cv. Okay, so PV to the power gamma equal to constant, and we have to calculate the work done. So simply you know that dW equal to PdV all the time, so your W will be simply PdV, okay, from V1 to V2, initial volume to final volume. Now just see that you have to take the integrand as V, so you have to integrate over V, right? Now you can convert your P into the form of V using this expression, where your P is simply A by V to the power gamma. So this is A by v to the power gamma dv from v1 to v2. Now because A is a constant, let us take it outside the integral and only integrate over dv by v to the power gamma from v1 to v2. This is A. Then integral result gives you v to the power minus gamma plus 1 divided by minus gamma plus 1 from v1 to v2. This is A. v2 to the power 1 minus gamma minus v1 to the power 1 minus gamma divided by 1 minus gamma. Okay. So this is the work done W. Now remember what are the informations you have in the question. So in the question you have information about the P1 and P2, but you have only V1, you do not have V2. So like in this expression you do not know the value of V2. So how do you calculate? Also you do not know the value of A. But you do know that A is nothing but the product of PV to the power gamma. So by that fact you know that P1 V1 to the power gamma will be constant. That is equal to A. And it is the same value will be P2 V2 to the power gamma. So P1 and P2 should be different, V1 and V2 should be different, but their product like this, P1 into V1 to the power gamma or P2 into V2 to the power gamma, this product value is constant as at A. So we just put down the expression for A using these both terms. So for the first term we will use this expression because then 2 and 2, so they will use for P2 V2 so that it gets simplified. So P2 V to the power gamma is the A value here, and then the second, this term is V2 to the power 1 minus gamma. Minus this time on the second term you use A in terms of P1 V1 to the power gamma because then only it cancels out this second V1 term. This is P1 V1 to the power gamma into V1 to the power 1 minus gamma divided by 1 minus gamma. So this is P2 V2 to the power gamma plus 1 minus gamma. So this gamma and minus gamma cancelling out and only giving you V2. So this is P2 V2 minus V1 to the power gamma plus 1 minus gamma. So this gamma and gamma also cancelling out and giving you P1 V1 divided by 1 minus gamma as it is. Okay. So now you see you have simplified it a lot, that you now do not have this like gamma terms, but there is one problem still left, that you do not know the value of V2. So first you have to know the value of V2 from your known information, and then you can get the final result. So this is easy because you know that this P1 V1 to the power gamma is P2 V2 to the power gamma. So from it you can convert that V2 equal to P1 V1 to the power gamma by P2 to the power 1 by gamma, because there was P2 V2 to the power gamma, so you have to take that out. So this is simply P1 by P2 to the power 1 by gamma into V1 to the power gamma by gamma, which is just 1. So V2 is equal to P1 by P2 to the power 1 by gamma into V1, right? So you just substitute it here. So this is P2 P1 by P2 to the power 1 by gamma into V1 minus P1 V1 by 1 minus gamma, right? So there you have P2 to the power, let us not like rearrange terms anymore because that will make it even more complicated, but rather now just look at the expression that now you have all the terms that you know already the values of, like you know P1, you know P2, you know V1, you know gamma. So everything is known. You can just substitute the values now and you will get the final answer. So you have successfully converted the unknown parameters into known parameters, and you can now calculate the work done. So your P2 is mentioned as 1 atmosphere. So P1 is 8 atmosphere. This is 8 by 1 into 1 by gamma is 1 by 1.5 into V1 is 1 liter. So this is 1. And again P1 is 8 atmosphere and V1 is 1 liter divided by 1 minus gamma is 1.5. Now remember this is liter atmosphere, because this is P into V and gamma has no unit. So P is in atmosphere and V is in liter. So this is liter atmosphere unit that your work done is calculated. And later on you have to convert it into joule, because the question asked you to get the work done in joule units. Okay, so this is 8 to the power of 1.5 minus 8 divided by 1 minus 1.5 is minus 0.5, right? So this is 8 to the power 1.5, it will give you just 4. So 4 minus 8 by minus 0.5, which is minus 4 by minus half. So this minus and minus cancelling out. So this is just 8 liter atmosphere. This is the work done. Okay. So if you have to convert it into joule, so liter is nothing but decimeter cube. So this is decimeter cube into atmosphere. Now you have to convert into joule, that means all in SI units. So decimeter cube will have to be converted into meter. So 1 meter is equal to 10 decimeter. So 1 decimeter cube is 10 to the power of minus 3 meter cube. And 1 atmosphere is simply 1.013 into 10 to the power of 5 Pascal. Pascal is the SI unit of pressure. So by multiplying this factor, you will get 810.4 joule, which is nothing but meter cube into Pascal. So this is your answer. This is option number A that you have obtained. You can also calculate by using your calculator and you will get the same answer. So let us go back. So the answer is closer to this one. So this A option is correct. Right. Now, question number 4. Question number 4 is that a gram mole of helium at 20 degrees centigrade is suddenly subjected to a pressure of 10 times its initial value. Find the final temperature momentarily attained. The ratio of specific heat is given by 1.67. So first of all, understand the problem. You have 1 mole of helium, so N equal to 1, and the gas is helium, okay, and the temperature is T mentioned as 20 degrees centigrade. You can convert it into Kelvin, and it is subjected to a pressure suddenly. So focus on the word called suddenly, because this will be important. And the pressure is finally 10 times the initial value. That means if your initial pressure is P1, your final pressure is P2, then P2 is simply 10 times P1. And this T is 20 degrees centigrade is your initial temperature T1, and the final temperature of the pressure after the pressure has been increased 10 times, you have to get the final temperature T2, because that is the question they have given you. So T2 equal to what? And the additional information is the ratio of specific heat gamma equal to 1.67, which is like Cp by Cv. Okay. So here the point I was telling you about, that you have to focus on the word called suddenly. So wherever the suddenly word has appeared, that means the whole process has occurred much quickly or suddenly, and so quickly that it basically means as if the system has got no time to exchange any heat from the surrounding or in between the system and surrounding. And so in this process the heat has been remained constant, or your dq equal to 0. That means no heat has been either absorbed or released. So that is the idea of adiabatic processes. Adiabatic processes are always not about the speed, whether it has happened quickly or very slowly, that does not matter. But the main condition is that whether the process has restricted the heat exchange, that means dq equal to 0, then only you call it an adiabatic process. And where this gamma terms becomes important, because then the equation becomes Pv to the power gamma equal to constant, or some other relations between the other thermodynamic quantities, the main three quantities of temperature, volume and pressure, but it always involves the specific heat ratio or gamma. Okay. So these are the information that you have got in this question, and now you try to solve this question by those known informations, right? So this is question number 4. N equal to 1 mole. T1 is the initial temperature equal to 20 degrees centigrade plus 273 Kelvin is equal to 293 Kelvin. And your initial pressure, let's say this is P, and our final pressure is just 10 times the initial pressure, which is simply 10 P, let's say. V1, sorry, V1 is not mentioned. So final pressure you have, final temperature you have to calculate what is T2 after the expansion. Sorry, not the expansion, but the pressure increased to 10 times just after gamma is equal to 1.67. Okay. Now because this process has happened suddenly, that means it has happened so fast that no chance for any heat exchange system and surroundings, right? So your dq equal to 0 simply. That means it is an adiabatic process. But remember that this is not the sufficient condition for calling it an adiabatic process, because it has not so much to do with the speed. It is just by terminology that if this has happened so suddenly, that means there is a very less chance of heat being exchanged, so it is an adiabatic process. But because we are confirmed now, because they have also mentioned as the value of gamma, that also gives you another hint that you have to use the adiabatic process rules. And so the main rule we all know that PV to the power gamma equal to constant, right? So the relation between pressure and volume. But the other quantity, temperature, is also another quantity. So it can be in relation, that like pressure and volume, you can find a relation between pressure and temperature, or you can also find a relation between temperature and volume. All these can be possible just from this one equation. And also because this is an ideal gas, this is mentioned in the problem that this is an ideal gas and 1 mole. So that means ideal gas equation will also be valid, that is PV equal to RT for 1 mole. Now in the problem, you have information about the initial and final pressure and the initial temperature, and you have to calculate the final temperature. So very clearly you have to know the relation between the pressure and temperature, so that you can get the final temperature value using the other values, right? So this is a relation between P and V, but you find a relation between P and T, then only our problem will work. So how do you do that? Basically you have to replace this V by some quantity that is related to P and T, and the easiest way out is this. So this V can be written as RT by P. Okay, so now this volume has been represented in terms of a constant R, the temperature T, and the pressure P. So that is what we substitute here, that P equal into RT by P to the power gamma is equal to constant. So it's P into P by P to the power gamma, T to the power gamma is equal to constant. We take this R to the other side and take it, absorb it inside the whole constant. So that is not a problem. So this is T to the power gamma by P to the power gamma minus 1 is equal to a constant. So this is the relation you have got between T and P for the adiabatic process, right? Now you can calculate what your T2 is using this formula, this relation. So basically T1 to the power gamma by P1 to the power gamma minus 1, because the right hand side is constant, so this will be like T to the power gamma by P2 to the power gamma minus 1. Now remember you have to calculate T2. So this T2 by T1 to the power of gamma equal to P2 by P1 to the power gamma minus 1. So this T2 equal to T1 times P2 by P1 to the power gamma minus 1 by gamma. So this is just T1. So P2 is 10 times P1. So this is 10 P1 by P1. Gamma minus 1 by gamma is simply 1.67, the gamma value. 1.67 minus 1 by 1.67, and the T1 value they have also mentioned that this is 293 Kelvin. This is 10 to the power 0.67 divided by 1.67. So now if you use your calculator, this is a simple calculation that this will give you 738 Kelvin. From here you have to convert into degree centigrade. So this is 738 minus 273, which is roughly 465 degree centigrade. So this is your answer. The final temperature is under this process, after this process of pressure shooting up 10 times of the initial value in this adiabatic Sardan process, the final temperature is 465 degree centigrade. So this is 465 degree centigrade, which is option number D. So this is correct. Okay. Now we move on to question number 5. This is also a small problem. And again you have problem about the adiabatic expansion process of an ideal gas. And you have to calculate what is the value of delta P by P, and the options are all given in delta P by P unit. So you have to use the adiabatic method relation between pressure and volume, and from there you can calculate this thing. So let us go and check what the answer should come. So problem number 5, they said that this is the adiabatic expansion of ideal gas. So this is following a rule, PV to the power gamma is equal to constant equal to A. Okay. Then the derivative of left hand side is equal to derivative of right hand side equal to 0, because right hand side is a constant. Now take part by part derivative on the left hand side term. So first let us take the derivative on P. So this is V to the power gamma dP. Then keep P constant and take the derivative over V. So this is V to the power gamma derivative will be like gamma P to the power gamma minus 1, then dV equals to 0. So this dP is equal to minus, so this P to the power gamma dP equal to minus P gamma P to the power gamma minus 1 dV. So now dP by P equal to minus gamma P to the power gamma minus 1 by P to the power gamma dV, or your delta P by P equal to minus gamma. So this is gamma minus 1 minus gamma, that means just this is gamma minus 1 minus gamma dV. V to the power minus 1 is 1 by V, so minus gamma by V dV. Or you can convert this dP as delta P also, because both are change in pressure. So delta P by P is equal to minus gamma, same dV, change at delta P by V. So this delta P by P is answer coming out as minus gamma delta V by V. So this is your option number B as per the options given there. So let us go back and check. Okay, so this is option number B is the correct answer, right? Okay, so question number 6 is about, in a cyclic process the change in internal energy of a system over one complete cycle is. So the simple answer will be 0. Why 0? I will explain that here only, because this is not a too much of a calculative sort of question. This is a descriptive question. So cyclic process, by I'm sure you know by now that cyclic process is something like you start at one point, then you go on to the process, and then finally you come back at the same original point that you started at. So here your initial point becomes your final point. At a cyclic process, it goes on like a cycle, as in your initial state becomes your final state. So you go through that process and come back to the point where you started at. So initial is equal to final, and this internal energy, that is u is a state variable. So like temperature, like this, because u is a temperature dependent quantity also, like work done and heat energy, these are not state dependent but they are path dependent quantity, but this u is a state dependent variable. Okay, that means it depends on the state the system is at that moment, right? So let's say if we draw a cyclic process in a PV diagram, where this is P axis, this is V axis, this is one point, this is another point, this is, let's say, 1, you start at 1, then you go from 1 to 2 like this, then again you come back to 1. So this becomes a cyclic process where you start from 1, go through 2 and again come back at 1. So this is a cyclic process. Okay, but the trick is that in this process the work done is not zero. Like this dashed blue part that I am drawing right now, this is the area under this curve, right? Area under PV diagram, and this will give you your work done, or W. So basically you see that in a cyclic process your work done is non-zero. Okay, W it is non-zero, but U equal to, sorry, this is not W, this should be dW, because otherwise it may create confusion. I mean to say that the work done that is particularly happening because of this stress is not the net work done, but right now because the change in internal energy is zero, not the internal energy is zero, because internal energy is temperature dependent quantity, so it cannot just be zero just like that. We are talking about the change in internal energy, or U, that is happening because when the system is going through that cyclic process. So in that case this dW is not non-zero, because W is a path dependent function similar as U, Q. So W, Q, this heat and this work, these are also energy, but these are path dependent variables, not state dependent. But U, which is the internal energy, that is state dependent. So whenever you are dealing with a path dependent quantity, so it does not matter whether you go and come back to the same point again. What matters is that a path has been traversed, right? So 1 to 2 and then 2 to 1. So this path has been taken, and because of that you have a finite non-zero work done or a heat energy. So dQ is non-zero and dW will be non-zero in the cyclic process. So this extra cut sign in the D means, or this sets apart these two variables from the normal variable like U, because these are path dependent. But du we do not write with the cross, we just write du because this is state dependent. Okay, so this is a sign to separately identify which quantity is path dependent and which is state dependent. So based on that, when you are coming back to the same point, that means it is a state dependent quantity, so your initial point minus final point value has to be subtracted. So in this cyclic process your final point U is UF minus your initial point U is UI, and because I and F are the same point, so this UF equal to UI and this becomes 0. So U is non-zero but du is equal to 0. That means in a cyclic process the internal energy does not change because you are going and coming back at the same point, and U depends only on the state. So if your state has not changed after that process, then the change in internal energy will also be 0. So this is the answer. Okay, hopefully this is clear. Then question number 7 is, how much external work has to be done to raise the temperature of 1000 gram of nitrogen from minus 20 degree centigrade to 100 degree centigrade at constant pressure? Take specific heat at constant volume CV as 21 joule per mole Kelvin, and R value is also given. So you have to here calculate what is the work done W. You need to raise the temperature. T1 is given as minus 20 degree centigrade and T2 is 100 degree centigrade, and this is happening at constant pressure. The specific heat at constant volume is given and R is given, and you have to calculate the W. and 1000 gram of nitrogen. So from here you can calculate what is a mole number for this amount of nitrogen, right? So this is the whole point of the problem. Now let me again solve this elaborately. This is our question number 7. Okay, and so just 1 second. So are we in the same question? 5, 4, 6, 7. I think there is, just let me check once. Sorry, so I went on to entirely wrong question basically. So there is a slight confusion because I mixed up this previous assignment with the current assignment. So let me just divide so that there is no further confusion. So up to this part, up to here, this previous week's assignment ends here, and from here this is current week's assignment. So current assignment for week 7. So this I'll also solve, but after I solve the previous part, and this part that I am dealing with right now is the earlier assignment, or this is a practice assignment. This is not the current assignment. Okay, not the currently given one, so do not confuse. So because the questions are similar, some of the questions I got confused. So let me just take off from where we, so basically this question was similar, because of which I got that confusion. So it's okay because this is the same question. So this is already we have solved, we have explained why this is 0. So this is the accepted answer, right? So this is done. So let me now first solve this, and then we'll go back to the, then we'll move on to the next set of questions. That is the current week's questions. So this question number 7 is, calculate the work done by 1 mole of a gas during a quasi-static isothermal process expansion from a volume of 3 V0 to 11 V0 when the equation of state is P V0 minus V minus V0 equal to RT. So the equation of state is given, and it is information is given that it is isothermal, and the temperature, constant temperature, is 27 degrees centigrade, which is basically 300 Kelvin, and the volume is expanding from V1 to V2. These values are given, and the number of moles of the gas is also given as N equal to 1, and you have to calculate what is the W, right? So now let me solve this. This is also question number 7. So our system has number of moles 1, and your temperature is constant at 300 Kelvin, which is 27 degrees centigrade. This is constant because this is an isothermal process. Okay, and your equation of state is given in the question as P V minus V0 equal to RT. So see that this is the equation of, this is not the ideal gas equation of state, because that is only PV equal to RT, but they have specified a separate equation of state, and this you have to use for this case. Okay, now you have to calculate what is work done. So you just take an integral over dW, right? So this is, you know, that generic expression is PdV, right? Now PE is something you have to take from the equation of state, because P is unknown here. So P is equal to, written in terms of RT by V minus V0. So this is just RT by V minus V0 to dV. So this is just RT dV by V minus V0, right? Alright, so this is RT ln of V minus V0, and here remember that you have to take the integral from initial volume to final volume, which is also given in the question, that initial volume was 3 V0 and then finally it is expanded into 11 V0. Okay, so you are going from 3 V0 to 11 V0. So this is just RT ln of 11 V0 minus V0, right? Basically because it is ln, so we can take it like this. You can directly divide these two. Ln of x minus ln of y is basically ln x by y. So this is 11. Okay, 11 V0 minus V0, 3 V0 minus V0. So this is just RT ln of, this is 10 V0 by 2V naught, which is like RT ln 5, right? Now we can put the values of R, which is 8.314, and temperature is given as 300. So this is in joule per mole Kelvin, okay? And ln 5 you can calculate by using your calculator, and finally you will get this value, which I have already calculated. You can check for yourself that this is 4014 joule, as I have used the joule per mole Kelvin unit. So this is your answer. And you can check that this is the option number C that they have mentioned in the options. Let me mark that option. Sorry, yeah, so this problem said 4014, so we have got 4014, this is 4012, close enough. This is because some little bit of order, this is in the same order approx, but some change are possible. We have to find the closest possible answer. So our answer is actually correct. So that is option number C. It is solved. Now move on to question number 8. It is saying that an ideal monoatomic gas and diatomic gas is adiabatically expanded from pressure volume of PiVi to final pressure volume of PFPF. Then find out the ratio of work done for the monoatomic and the diatomic gas. So you have two kinds of gas, one is monoatomic and the other is diatomic, and the process is adiabatic expansion. So you already know that if the process is adiabatic and you have the information about pressure and volume, so the immediate relation you have to remember is that PV to the power gamma equal to constant equal to A. That is a relation you have to use here as well. Just this gamma value, remember this gamma value will be separate for a monoatomic gas and a diatomic gas. So this calculation we have already done in earlier weeks of the lecture and the assignment sets, because there you had to calculate how to calculate gamma or specific ratio when you have information that the gas is monoatomic or diatomic. So we can do that again now. Even I can show it quickly how to calculate, but probably you remember, and you can then put the gamma value differently. But remember to put the gamma value differently because the gases are different. One is monoatomic and the other is diatomic. But what similarity they have is that their initial pressure and volume is PiVi for both, and final pressure and volume is also PFVF for both. Now because the gamma value is different, only even if the initial and final volume and pressure are same, but the work done will be different for monoatomic and diatomic, and we have to calculate the ratio of that work done. Also this is an adiabatic process for both of them. So let me now solve this. That, yeah, so here question number 8. First of all, this is an adiabatic expansion process where the main relation you have to use is PV to the power gamma equal to constant, where gamma is the specific heat ratio Cp by Cv. Now gamma is different for monoatomic. We mark it as gamma m for our simplicity, for the simplicity of writing and identifying, and the gamma for diatomic is also different, which we mark here as gamma D, suffix D and suffix M for monoatomic and D for diatomic. Now you probably remember in the earlier lectures where we studied the kinetic theory that gamma is 1 plus 2 by F, where F is the degree of freedom of the gaseous system. Now if it is a monoatomic case, you know there is a single atom and no constant at all. So then the degree of freedom is just 3, which is the dimension of 3 into number of atoms n, capital N, minus m, which is the number of constants. And for monoatomic the number of atoms is 1 and no constant at all to restrict it. So because there is only one atom, so 0. So this is just 3. That means it is like free to move in all 3 directions, x, y, z. So F is 3, and for that gamma m is 1 plus 2 by 3, that is 5 by 3. Then for diatomic, what happens is that diatomic, the degree of freedom F equal to 3 into 2 minus 1, because here the number of atoms n is 2, and because 2 atoms are having a bond in between them, so that is the constant in this case. So this is the m equal to 1 constant between the 2 atoms for diatomic, and hence it is 1. So this is 6 minus 1, 5, and similarly the specific heat ratio gamma D will be 1 plus 2 by F, 1 plus 2 by 5 is 7 by 5, right? So we have calculated both of them. Now your initial and final pressure and volume is Pi Vi to Pf Vf for both. Now you just have to calculate the work done. So you have to know what is the work done for adiabatic processes. So adiabatic work done, how to calculate that? You again have to use this PdV as an integral from V1 to V2. But right now your PV to the power gamma is equal to the constant A. So your P is equal to basically A by V to the power gamma, right? So you put that, A is constant, so it comes outside. So this is dV by V to the power gamma from V1 to V2. Or in this case, Vi to Vf, because here the initial and final are marked by Vi and Vm. So this is A, then V to the power minus gamma plus 1 divided by minus gamma plus 1 Vi to Vf. So this is equal to A by 1 minus gamma Vf to the power 1 minus gamma minus Vi to the power 1 minus gamma. Now you again substitute the value of A here. A can be written as Pf Vf to the power gamma into this term, Vf to the power 1 minus gamma, minus again P can also be written as Pi Vi to the power gamma, because ultimately this is a constant which is a product of PV to the power gamma. So it does not matter whether you use the initial state or final state. We use like that here because we can then cancel out some of the terms and look the whole expression look more compact and more close formed, right? So this is the second term is Pi Vi to the power gamma into Vi to the power 1 minus gamma divided by 1 minus gamma. This is Pf Vf minus, because this gamma and minus gamma cancelling out, so this is Pf Vf minus again Pi Vi divided by 1 minus gamma. So this is your work done for adiabatic process in general. Okay. Now you have to take the ratio for monoatomic and diatomic case. So what to do is now is Wm monoatomic work done divided by diatomic case work done. So you see that this term will be same for both of them because their initial and final state parameters are just the same as per the question. So this term we do not bother about. This will be cancelling out in the ratio. The term which will be different is the denominator, right? So this term is different because gamma is different for monoatomic and diatomic. So we only deal with that in the ratio. And since this is inversely proportional to the work done, so Wm by Wd will be 1 minus gamma d by 1 minus gamma m. And this we have calculated. Gamma d was 7 by 5 and gamma m was 5 by 3. Right? So gamma d is 7 by 5. Gamma m is 5 by 3. So this is minus 2 by 5. This is minus 2 by 3. Minus and minus cancelling out. So 2 by 5 into 3 by 2. So this is just 3 by 5. Okay, which is like 0.6. Now let us go back and check 0.6 is the answer or not. Yeah, so 0.6 is our option number B. Option number B is the correct answer. So this is not when like shown in here, but B is the correct answer. Okay, now we have two questions left, 9 and 10. 9 says that the temperature of 1 mole of gas is raised to 100 degrees centigrade from 20 degrees centigrade via a polytropic process where N is 1.4. So first of all, polytropic process, probably you know that polytropic means you have an equation like PV to the power N equal to constant. So this is a generalized form. Polytropic means this N value is not 1. Generally, when N value is 1, which is the simplest case, but polytropic means N value is more than 1 basically. And for like adiabatic case, N value is gamma, so then it becomes PV to the power gamma equal to constant. But polytropic is in a more generalized sense where we always do not mention what is the N value. It can be gamma, it can be anything else. But this is just polytropic means you have to know that this is the relation they will follow, that PV to the power N equal to constant. And they are mentioned in the question that N exponent value is 1.4. And the number of moles of the gas is also 1, N equal to 1. T1 is 100 degrees centigrade. Sorry, T2 is 200 degree. T2 is 100 degrees centigrade. This is the final temperature, and T1 is the initial temperature, which is 20 degrees centigrade. And you are keeping the pressure constant. Then you have to calculate what is W, right? And you have the information that this is a polytropic process. So let us solve. So you will see that this is very similar to how you calculate the adiabatic work done, just instead of gamma you have n as the exponent, right? Otherwise things will be similar. So we'll see that first of all, number of moles n equal to 1, T1 is equal to 20 degrees centigrade, T2 equal to final temperature 100 degrees centigrade, and pressure is constant or fixed, it does not change. Polytropic process. Polytropic process means it will follow a general equation Pv to the power n equal to constant equal to A. And n value they have, sorry, this n, do not confuse this n with this n because this is the number of moles. Okay, so my bad, because they are another, so this another n. So I'll just call n as this exponent of the polytropic equation, and number of mole is just taken as number of mole, and this is equal to 1. So do not get confused by that. And n is equal to given as 1.4, right? Now the work done. So work done is again integration dw from T1 to T2 because that is the change in state from 1 to 2, initial to final. And W is dw is pdv, right? So right now I am not putting the integration limits because your integrand is v, so you have to take the initial and final limit in v terms only, but later on you'll see that we'll convert the whole thing in temperature terms so that we can put the final and initial limits that are known that are of the temperature values. Okay, so now this pdv, now Pv to the power n is equal to constant, so you write P is equal to the constant A by V to the power n. Similarly, just we had written for adiabatic for n equal to gamma. So I'll just quickly solve this because this is already solved. This is a similar solution I have just done right this before this problem. So is constant outside integral dv by V to the power n, right? So this is A, V to the power minus n plus 1 by minus n plus 1. And this is state 1 to state 2. Now you do not know the values of V1 and V2, so I am just generally writing it as 1 to 2 as the two limits. Now this is just A by 1 minus n, V2 to the power 1 minus n minus V1 to the power 1 minus n. So this is final volume and initial volume. The values are not known to us. But we do know that P1 V1 to the power n is equal to P2 P2 to the power n is equal to the constant A. So we just put the value. This is P2 V2 to the power n, V2 to the power 1 minus n, minus P1 V1 to the power n, P1 to the power 1 minus n divided by 1 minus n. So this is just P2 V2 minus P1 V1 by 1 minus n, right? So if that is the case, then this is equal to now we have to convert this in temperature terms because temperature is something that we know the value about in this problem. So because this is an ideal gas, that does not change, right? So ideal gas equation is it has to follow, and this is for 1 mole, so just PV equal to RT will be the ideal gas equation. So your P2 V2 will be RT2 and P1 V1 will be RT1 divided by 1 minus n. So this is just R T2 minus T1 by 1 minus n. So this R is 8.314 joule per mole Kelvin into T2 minus T1 is the temperature difference, and you know that whether you take in Kelvin units or in degree centigrade units, but temperature difference remains constant. Temperature absolute value changes with what unit you are using, but temperature difference, that quantity remains constant no matter what unit you are using. So we'll just write just directly then take the difference in centigrade units only, because as I said the difference value will be the same, right? Whether you add a plus 273 with both or not, that will give you the same value. This is just 100 minus 20 will be then the value, right? And then 1 minus 1.4 was the n value of the polytropic process. So this is just 8.314 into 80 minus, because this is divided by 0.4 which is minus sign, so it comes up, and if you calculate you will see this is minus 1662.8 joule. So this is a negative work done. You can see the work done has come negative, and do not get puzzled by that. The work done should be negative here because this is the work done on the system, because this is the logic that we use in first law of thermodynamics, that if your first law of thermodynamics is saying that dq equal to du plus dw. Now if this is an adiabatic process, okay, so like here it is a polytropic process, so there is nothing mentioned about that. But generally, if this is an adiabatic process, so your dq becomes 0, so then du becomes minus dw. So that means the change in internal energy is giving you the work done. Or in other terms, because the system cannot take or give away any heat, so the only source of its work done is the expense of its own internal energy. And by that we mean that when the system is doing work, that means its internal energy will get reduced by that, so your du becomes negative, and that is when you call the dw positive, because du equal to minus dw. So if du is negative, dw is positive, and then that means the system is doing work by itself, or this is work done by the system, right? But then when your dw is negative, then we mean that the work is done on the system, because that is when your du becomes positive when dw is negative, and du positive means system internal energy has been increased by that process of work done, or in other terms, some external agent is doing the work on the system, that is why its internal energy is not like it is not used, but its internal energy is enhanced. So but in this case it is a generalized form, it is a polytropic process, nothing mentioned about the heat not being exchanged or anything, but just for the idea I was saying that the work done can be negative on this case. I am not giving we do not need to give any explanation to this minus sign here, because this is not what we have been asked in the question, but just I was giving an example for the context only. Okay, so this is our answer, and you can match the option. This will be option number C in question number 9 of the previous assignment. Okay, so right, so option number C is the closest, because we have got this 62.8. So this is the correct answer. Then the final question is a nice question, because here you deal with a slightly different, like changed aspect, but this is also a thermodynamic system, but instead of pressure and volume you are dealing with other quantities. So let us read the question first. Now the equation of state of an ideal elastic substance is given by this F equal to given by some terms of K, T and L naught, etc., where F is the tension of that object, K is the constant, L naught is the value of L at zero tension, is a function of temperature. So L naught is a function of temperature. Find the expression for the work done required to change the length L from L naught to 1/3 L naught quasi-statically and isothermally. So just notice that until this point we are only dealing with pressure and volume and this fluid kind of system which has quantities like pressure and volume. But the same thermodynamic system ideas can also be applicable for the solid, where the quantities will be different, because it is a solid, it is not having the pressure, volume, these kind of things, but or in other terms this is not relevant quantities to define those systems. So here we have equivalent quantities, and in this case like it is tension of the object and the length of the object. So like this is an ideal elastic substance, so you can think of it like a wire or something, solid wire. So that wire will have a tension, force. Tension is basically some kind of force, you can say. So this tension is F, that is one quantity, and the other variable or other quantity is length L. So just like, because we can categorize it in intensive and extensive variables, so just I am quickly mentioning it. What are they? So any thermodynamic systems, you have two kinds of variables to define the system properly. One is intensive variable and other is extensive. Intensive means the quantity or the variable is independent of the mass or the number of particles present in the system. Independent. Intensive stands for independent. So that means like you can say, for example, pressure is independent of how much mass the system has. Okay, just like in this case you have tension, which is independent of the mass the system is having. These are intensive quantities. So for high like a fluid type of a system like liquid or gas, it has pressure as an intensive quantity, and the extensive quantity is something that is dependent on the mass or the number of particles in the system, like volume. In this case, for a fluid the volume depends on the mass, okay, so or the number of particles, that as it is proportionate to that. It is a quantitative matter, so that depends on that, but pressure is completely different, it is intensive. Similarly, for a solid object like a solid elastic wire or something, it is tension is the intensive quantity, and length is the actually measurable variable, which is extensive because it depend on the actually we can quantify that for that system. So always not, you cannot always say the mass, but actually which is dependent on the scales with the systems. What can I say, systems number of particles or something, it can scale with that. For example, if you let's say increase the number of particles or atoms which are present in a gas, so most likely your volume will also get changed, right? Because then it will expand, so your volume will get scaled by that. So but pressure can remain unaltered because pressure is intensive quantity. So just like that, but here what is important is that here the thermodynamic variables are force and length. So we can think of it equivalent to pressure and volume kind of a system, but instead of P and V we now shift to F and L, but otherwise the whole concept will be the same. Just same as I mean that just like here you used to calculate work done by PdV because that is the convention, work done is calculated by that. But in this kind of a system, W is equal to also a similar integration, but here there will be a minus sign. This is just for the convention, how you define your work done. For this kind of systems, your work done is defined like that, but to follow the same convention you have to put a minus sign for this thermodynamic system with F and L as the thermodynamic quantities. But it is again the integration type is same, that the intensive variable is remaining at the first, and the integrand is being taken over the quantity which is extensive, like here the volume and here equivalent is length. Okay, and then integral is being done. So because in the question they have mentioned the f in terms of in function of as function of L, so you can easily take the integral of FdL and integrate over all the L terms. And because T is a constant, because it is isothermal, so it will not get integrated, and K is all of course a constant, L naught is a constant, so these terms will not get integrated. And your initial limit and final limit is also given. For L1 is L naught and L2 is 1/3 L naught. So you just have to carefully integrate it out and you will get your final answer. So let us calculate this, that your question number 10, the last question of previous assignment, which is like 10 is W equal to minus FdL and L is changing from L1 to L2, where L1 is equal to L naught and L2 equal to L naught by 3, right? So this is minus KT L by L naught minus L naught square by L square dl, from changing from L naught to L naught by 3. So this is minus KT 1 by L naught, this integral is giving you L squared by 2, minus L naught square, this integral is given by minus 1 by L, and this integral limit is L naught by 3 and L naught. So this is minus KT 1 by 2 L naught, then L square, putting the limits, is L naught square by 9 minus L naught square, minus and minus making it plus, so plus L naught square to 1 by L naught by 3 minus 1 by L naught, which is minus KT 1 by 2 L naught into, this is minus 8 L naught squared by 9 plus L naught squared, this is 3 by L naught minus L naught, so this is 2 by L naught. Okay, so you can cancel out some of the terms, so this is minus KT, 2 and 4, 8 is 4, so minus 4 L naught by 9 plus 2 L naught, and this is minus KT, L naught is common, so this is minus 4 by 9 plus 2, so this is minus KT L naught to 9 minus 4 plus 18, this is minus KT L naught into 14 by 9, so you are getting minus 14 kT L naught by 9. So this is your option number D. If you can check that this is the option number D in the previous question. Yeah, so with this we solved all of the questions in the practice assignment. Now you move on to the current assignment. So as I said, some of the questions will come common, so we'll not do that. We'll just do the questions that are not repeated. Like question number 1 is common, so this is already done. I'll not do that again. Question number 2 is something new and interesting, so that I'll solve. So let us start with that. So they have given a graph of P versus V here where different points are marked. 3 such points are A, B, C and B. And it is saying that the number of mole N equal to is 1 and it is a monoatomic ideal gas. Okay, and it is taking a path from point A to another point B along the path ACB. So it is going from A to B, but not directly, but through via C. So it is first going from A to C and then C to B. So your total journey or total process contains two steps. One is A to C and then one other is C to B. Total is forming this ACB path. Okay, and the initial temperature at T naught here, that at A the temperature is T naught. Calculate the heat absorbed by the gas in the process. So in this whole process you have to get what is the Q or heat absorbed in the whole process. So this is a PV diagram. First of all, you know that you can always get the work done by information about the PV diagram, or because always you do the work done by the integral of PdV, right? So basically it is somewhat like area under the PV curve. But here, because this is the discrete sort of points are given, so you can take your whole work done, you can calculate your whole work done in this process ACB by dividing into two parts, AC and CV. And similarly, you can also calculate what is the change in the internal energy of the system in the path AC and then in the process CV, right? So this whole thing can be calculated. Okay, so we are discussing this question that from the same PV diagram we can calculate both the work done and the what is to say that internal energy change in that whole process from A to C and C to B, and then adding those two up we can always get the heat that is being absorbed in the process, because you know first law of thermodynamics is dq equal to du plus dw. So if you have to calculate dq, you can always get separately what is du and what is dw and then add them up and you can get the whole heat absorbed thing. Okay, so now let us go through the process step by step. So now right now we are starting with the current week's assignment. So this is our current assignment 7, right? So and we are discussing question number 2, which involves this PV diagram. So let me roughly draw it, so that may not be very accurate, but you will get the idea. This is point A, point C and point B. This is V naught and this is at 2 V naught, and here this is P naught and this is 2 P naught. Okay, so you are talking about the process A to C and C to B. So you are finally reaching from A to B via C. So this is our process, and at A the temperature is T naught. At the other points the temperature is not mentioned, that you have to calculate. So at A, if you trace out on the PV plot, you will see at A the values are P naught V naught. At C the values are P naught comma 2 V naught, and at B the values are 2 P naught comma 2 V naught. So at every point you have information about the pressure and volume, but the temperature information is only given at the point A. Other 2 points are not specified. Now first of all, we'll calculate the total work done in the process. So as I mentioned to you earlier that work done is basically a path function. So work is basically a path function, right? So it depends on the path that is taken and not the initial and final state. So obviously the dW, the total work done, will be a combination of work done on the two steps of this path, which is like dW in the path A to C plus dW in the path C to B. This forms the net work done in ACB process. Okay. So by that scenario, you see that now let us characterize each of the steps. Like this A to C, this process can be an individual process where the pressure is being constant, because you see on this AC line, on this AC line, if you go by this line, you will see that the pressure is constant throughout, and this is constant as P naught. So in A to C, the pressure is constant as P naught, and the volume is changing from V naught to 2V naught. Okay. So this is an isobaric process. This is a constant pressure process, isobaric process, and is expanded from A to C as the volume is changing from V naught to 2V naught. But this is isobaric. Okay. But in C to B, the second step of the process, here you can see that the volume is constant and pressure is changing, because on this line the volume is 2V naught equal to constant, and the pressure is changing from P naught to 2P naught. And you know that constant volume process you call isochoric process. Okay. Yeah. So isochoric process. So this is a combination of isobaric and isochoric, these two processes, and we are dividing it into steps for the simplicity of the problem, because then we can very easily solve this, and step by step we'll just have to follow the different steps. Okay. Right. Now, so this AC, because we called that this is a constant pressure isobaric process, so you know that this will be like PdV, right? The simple expression of work done, PdV, from V1 to V2. And the second step is also PdV, and sorry, here this is on the process AC and this is on the process CB, both are different. So even if I am generally writing the limit as V1 to V2, the limits are not the same for both of the cases. Please remember that, because the process are different. So for the first case, because the pressure is constant, because it's an isobaric process, and the pressure is constant at the value P naught, so P naught is outside the integral, and dV is changing for V naught to 2V naught. So this is done. This is pretty simple. And the second process is an isochoric process where the volume is constant. So here you see the volume is constant. That means your initial volume is your final volume, which is C to B is 2V naught at the volume fixed. So initial limit is final limit, and PdV. So dV has no change. So even if pressure got changed, but dV has no change. So obviously this dV is 0, and the second part total work done becomes 0. So on the path A to C, you have a work done of P naught into 2V naught minus V naught, and the second path C to B, you have a work done of 0. So this is just P naught V naught plus 0 equal to P naught V naught, right? So this is the net W in the path ACB. So one part is done. Now we calculate the net internal energy change. So call it dW, because this is the work done. So some amount of work is done. So we call it dW for consistency, and net internal energy change in the ACB process. So that is the total delta U of ACB. We can again divide it into two parts. Similarly, A to C and delta U, the second process is C to D. Now, one thing to note is that you know that generally your du is just Cv dt, but Cv is the molar specific heat at constant volume. So that is by definition. So delta U will be like Cv into the temperature difference in from A to C. So Here the temperature at C we call it as Tc. So this Tc is not some transition point temperature, but this is the temperature at the point C. Similarly, Ta is the temperature at the point A. Okay, and the second case also you take the difference Cv into temperature at the point B, which is the final point, and the temperature at the point C, which is the initial point. So these are taken like that because we have already stated that U is a state variable, so it will depend on the state's initial and final state, and in this case it will depend on the initial and final state temperature. Now in the question they have mentioned that your Ta is given as T0, but you have no idea about what is Tb and Tc. So you have to get that, okay, first of all, or you have to express them in other terms, in some other known quantity terms. And how do you do that? First of all, you also have to get what is the value of Cv, right? Because you do not know the value of Cv, and only known quantities in this case are P0, V0 and T0. So all the terms that are unknown, you have to convert it into those terms. So first of all, you know the basic definition of Cv is that Cv is equal to du dt, and which is like half a far. So this you can remember from earlier lectures, from some earlier week's assignment. We have already solved this, that Cv can be written like this, half a far, where Cv is the molar specific heat at constant volume. This is molar because of which we have R here, and this is actually like derived from the starting from the equipartition of energy. This is all discussed in the kinetic theory chapter. So if you have forgotten, please go back and remember this part. But Cv is equal to half FR. That is a given to us, right? And this F is the degree of freedom. So in this case the question has mentioned, you remember that this is a monoatomic gas. Monoatomic means your F is simply 3 degrees of freedom and now no constant. So then Cv is like half 3R, right? And you know that Cp minus Cv, so we do not need to calculate Cp minus Cv. Basically you will only need Cv here, so directly just write Cv is equal to 3R by 2, right? So this is done. Now so Cv is done, so we have to get still the values of T, C and Tb because Ta is already known. So now we utilize the idea of ideal gas because these are ideal gases. So this will follow ideal gas equation. Now at point A, the ideal gas equation is like P0 V0 equal to R Ta. P0 and V0 is the pressure and volume at the point A that you can see from the graph very easily, and Ta is the temperature at A, which is P0 V0 by R. This is also mentioned as T0 in the question separately. Similarly at point B, because no matter what point you go to, but this is still an ideal gas, right? So this will follow the ideal gas expression. Now at P0 the pressure has remained, at point B the pressure has remained P0, but the volume has changed to 2V0. So this is P0 into 2V0 equal to R into Tb. So Tb is equal to just 2 P0 V0 by R. And at point C you have 2 P0. Here the pressure is 2 P0 and the volume is 2 V0. So 2 P0 into 2 V0 equal to R Tc, where the Tc is the temperature at C, which is like 4 P0 V0 by R, right? So you have already obtained Tb and Tc, and you know Ta also, all in known terms of P0 V0 and R. Also you have calculated Cv as 3R by 2. So just directly write that part. So you can also combine this and get even more like simple terms. Like you can take common Cv and merge this. So this is Tc minus Ta plus Tb minus Tc. So you just get, now you have this Tc cancelling out. So this is something that we should have guessed earlier also. I was going to say, but I thought, okay, let me show you that as I stated that U is a state function, right? So it does not matter what path you go through, whether you go through a via point of C or not, or you directly go from A to B, does not matter. It does not matter what path do you take. It only matters that you are at the initial point A and the final point B. Those are the 2 points based on which the calculation of the change of internal energy will be done, because that is a state variable. So that the same thing has been happened even if we have divided the whole path ACB at AC and CB. But unlike the work done case where both of the paths have been contributing to different work done, and it will give you a different work done if you do not go through C and go via a different point, because then the path will be changed and the path variable W will also get changed. But because U is a state variable, this C point has just got cancelled out, and in the overall expression of the internal energy change of this process, you have only two temperatures, which is the initial and final state temperature TB and TA. So this is what I was stating earlier, and this is also clearly seen from the mathematical calculation also, that for delta U, you just have to know what is TB and what is TA, and you are sorted. So you have already CV as 3R by 2, and you have TB as 2 P0 V0 by R, and you have TA as P0 V0 by R. So this is just 3R by 2 into P0 V0 by R. So this R and R cancelling out. So you just simply have 3 by 2 is 1.5 P0 V0. This is your delta U, right? And so I think I have made some mistake. Let me check. TB minus TA. Oh, sorry. So I have just missed the B and C point. So this is point C and this is point B. My bad. Because this is now the TC, this is TB, this is TC. So TB is 4 P0 V0 by R, not 2. So this is 4. So then this is giving you 3 P0 V0, and you are having 9 by 2 P0 V0, which is like 4.5 P0 V0. This is your whole net dW in the process ACB, or in, let's say, A to B. So net heat absorbed in the process is equal to du from, because it is state variable, so you are only mentioning the initial and final point and not the whole path of ACB, plus dW, this is a path variable, so you are mentioning ACB total path, and this is equal to 4.5 P0 V0 plus your dW was coming as simply P0 V0. So this is P0 V0. So the total becomes 5.5 P0 V0 is your final answer. So let us go back and check whether it matches or not with any of the options given. So yeah, so we have 5.5 P0 V0 done. So this is option number B is the correct answer. This is done. So question number 3 is something also not common from the earlier set of questions. So we'll solve that. Now because we are almost familiar with the same sort of questions, so some of the questions I just solved on the side, because this is similar pattern, only the values are different. Like for this question number 3, it is saying that mass of certain fluid is contained in a cylinder by means of a frictionless piston and occupies a volume of 2.5 meter cube when the pressure is 1.2 into 10 to the power 5 Pascal. The fluid is then compressed reversibly under conditions in which the product of pressure and volume remains constant. Calculate the work that must be done to reduce the volume of the fluid to 1.1 meter cube. So in this problem, you have information about the initial volume V1, which is this, the initial pressure P1, which is this. Now it is compressed such that the product of P and V remains constant. So this is the condition they have given to you, that you have P into V is equal to constant. Now your final volume is reduced to V2, which is also given. P2 is not given, unknown. But this is a known relation that they will follow. And you have to calculate what is the W in this case. So first of all, the simple thing that you will come to your mind whenever you are asked to calculate W is as integration over P dV from V1 to V2. Because PV equal to constant, let's say equal to some A, PV equal to A, which is a constant. So P is equal to just A by V from V1 to V2, right? And this is A ln V from V to V1. This is A ln V2 by V1, right? Now because A can be anything. A can be P1 V1 also, and A can be P2 into V2 also. But because you don't have the information about P2, so rather we choose to write A as P1 V1, because those two forms we already know from the expression. So this is P1 V1 ln of V2 by V1. Now you just put the values. Make sure that the units are all in the same SI unit, which they are already, because Pascal and meter cube all in SI units. So the values will be like P1 is 1.2 in 10 to the power 5 Pascal into V1 is 2.5 meter cube into ln V2 is 1.1 by 2.5, and if you take your calculator you will get a value of minus 2.5 into 10 to the power 5 joule. So this is the SI unit of work done, joule. So you can match your answer, that your answer is option number A, okay, which is the accepted answer. So that is already what we have already calculated. So this is the right answer. They have not mentioned the sign, but if you just go by the values, this is the value of the work done that we have also got. Now question number 4. Question number 4 is, it is also not common, but the pattern is common. So let me just quickly read that and solve it. So calculate the temperature of helium after adiabatic compression to 10 atmosphere pressure from initial condition of 1 atmosphere pressure and 300 Kelvin temperature. Assume the gas is ideal. So gas is ideal, obviously. Temperature is given, and this is adiabatic compression. So adiabatic means no heat exchange allowed, dq equal to 0. And the final pressure is P2 10 atmosphere, initial pressure is P1 1 atmosphere. And the gas is helium, which is a monoatomic gas, remember. Okay, so now we have to get what is the final temperature. As in, your initial temperature was T1, initial pressure is given 1 atmosphere. After the compression, the pressure is given, it has increased to 10 atmosphere. Now we have to also calculate what is the final temperature, T2. So in this problem, what is most common is that because it's the adiabatic process, obviously there will be a gamma involved, and the relation you have to choose based on what quantities you are asked to calculate and what quantities you already know. So this is current assignments question number 4. And for this case, you know that adiabatic processes formula has to be used, which is Vv to the power gamma equal to constant. But because they are asking a relation between P and T, so you have to express this in terms of P and T and not P and V. And how to do that? You simply use the ideal gas, because they are ideal gas assuming. So PV equal to RT is for 1 mole ideal gas, and V is equal to simply RT by P to the power gamma, because you want to write a relation connecting P and T. Now because R is a constant, you just take it out and put in the right hand side total constant term. We do not bother about that anymore. And you simply have T to the power gamma by P to the power gamma minus 1 equal to constant is your expression for the relation between T and P for an adiabatic process. Now, because this is helium is monoatomic, and we have multiple times solved for monoatomic case, the degree of freedom is 3, and so gamma equal to 1 plus 2 by F. So gamma for monoatomic case is 1 plus 2 by 3 is 5 by 3. Okay, so that is for helium. So your T2 to the power gamma by P2 to the power gamma minus 1 equal to T1 to the power gamma by P1 to the power gamma minus 1. So you have T2 by T1 to the power gamma is equal to P2 by P1 to the power gamma minus 1. So you have simplified T2 is equal to T1 P2 by P1 to the power gamma minus 1 by gamma. So T1 is 300 as mentioned. P2 is final is 10 atmosphere. Initial was I think 1 atmosphere. And gamma is 5 by 3 minus 1 by 5 by 3, which is 300 into 10 to the power 2 by 3 into 3 by 5. 10 to the power 2 by 5, you can calculate the whole thing. You will get a value of 7.53 into 10 squared Kelvin. So you can check your answer options, that this is option number D that we have calculated from here. So we have done a lot of problems, so we have to go much further. But this is the question, So we got 7.53 into 10 square. So the answer is option number D, right? Because this is 7, this is the closest one. Now question number 5 we have already done. This is common in the earlier assignment. Same with 6. This is also common. And question number 7. Question number 7. Yeah, question number 7 is not common but of the same type. So let me solve that quickly also. Okay, so question number 7 is about how much external work has to be done to raise the temperature of 1000 gram of nitrogen from minus 20 degree to 100 degree centigrade at constant pressure. Take specific heat at constant volume. Cv is equal to 21 joule per mole Kelvin and R is given. So you have to calculate W. Sorry, you have to calculate, yeah, W. So you know that the work done is dW equal to pdV, right? Now in this case, because this is an ideal gas, obviously, because if nothing is mentioned we'll assume it is an ideal gas. So P is nRT by V dV. N is the number of moles, R is universal gas constant, and temperature is something that is that is changing in this case, so we cannot write it like that. So you have to change the integrand from V to temperature, because dT is the changing temperature in this case. So we do not have information about V1 and V2, but we have information about T1 and T2. So let me write, let us use that. So like here, this is we can write V equal to nRT by P, and so dV equal to nR by P dt. Why only dt is taken, not on P? Because on the question they have clearly mentioned that they are doing at a constant pressure. They have given a constant pressure. So P has no derivative form. P is not getting the differentiated. This is simply constant. So you now change the integral from terms of V to terms of T, because we have information about that. So P into dV is nR by P dt. So these P and P cancelling out. Dt, because integrand is limit is T1 to T2, initial and final temperature. So this is number of moles into R. Dt is just T2 minus T1. So number of moles in this case, this is nitrogen given of 1000 gram. 1000 gram by 28 gram, because 1 mole of nitrogen gas is equal to 28 gram. So for 1000 gram, the number of moles is 1000 by 28 into R is 8.314 universal gas constant, into, because temperature difference does not matter does not depend on the unit. So simply from 100 to minus 20 to 100, the change in temperature is 120. So this is just, if you multiply everything, you will get 35.63 into 10 to the power 3 joule. So this is your final answer. So we have obtained final answer. This is option number C, marked. Now question number 9, this is common. This we have already done. The answer was C. We have obtained. Please go back and check the questions I have done earlier. And finally question number 10 is different, that we have not solved before. And this is interesting also, because this is slightly different kind of a question. So let us read that first. That a solid object has a density of rho and a mass m and the coefficient of linear expansion alpha. Then find Cp minus Cv at pressure P. Right. So basically, instead of a gaseous system or fluid system, you have now a solid object. Mass and density mentioned, coefficient of linear expansion mentioned, and Cp minus Cv you have to calculate when the pressure is mentioned. Okay. And this is an important question, so let us solve that. Important as in not as the same type that we have solved till now, little bit different. So this is a solid, mass m and density rho. So what is the volume? Because rho equal to mass by volume, so then volume in known terms will be mass by density. So volume is mass by density. And coefficient of linear expansion, what does it mean? for a solid. This is alpha given. So coefficient of linear expansion, let me first write down the mathematical term. This is 1 by L del L del T at F constant. Because you know, for a solid object, the thermodynamic variables are F and T, tension and the, F and L, tension and the length. F is the intensive variable, L is the extensive variable. So basically it means that it is basically how, for a unit temperature change, how much is the length change with respect to the original length. So this is the rate of length being changed by a change in temperature. That measure is given by the coefficient of linear expansion, and this is the mathematical expression for that. Now from here you can easily get what is the coefficient of volume expansion, because here we have to also deal with volume, because ultimately it is mentioning about this whole rho and m, so the volume gets involved in this. So better let us calculate the coefficient of volume expansion, and you will know why I am solving for this, because there is a connection that you'll see. So coefficient of volume expansion, let us call it beta, which is the standard identifying sign we use for coefficient of volume expansion. So beta is of the same logic, that this is 1 by V del T at pressure constant. So this is coefficient of volume expansion. Now you know that in simple terms for a solid, you can directly write V is equal to L cube, considering this is a cube of each side length L. This is the simplest expression. So V equal to L cube, so you can write this as 1 by L cube, and del T is del T of L cube at some constant pressure, whatever. And you can, now pressure is also related to the force or tension, because pressure is nothing but force per area. So you can write in other terms this force equal to constant. So everything in terms of F and L. So 1 by L cube, this is 3L squared del L del T at F constant. So this is 1 by L del L del T at F constant. So just remember, this term is the same as the expression of coefficient of linear expansion, or alpha. So you are getting the coefficient of volume expansion is 3 times the coefficient of linear expansion alpha, or beta equal to 3 alpha. So this is already obtained. Now let us go back. What we need to calculate here is Cp minus Cv. Now you can find it out from the book or from the lecture itself, that Cp minus Cv has a generic term or generic expression that you can use directly here. From the thermodynamic variable, from the first law of thermodynamics chapter, you can directly find it. So I will not calculating it explicitly, just find out this relation, or you can try by yourself, and if you do not get the direct relation, then you can tell me and I can show you in the next class. But Cp minus Cv is generally P plus del U del V at T constant, then del V del T at P constant. Remember, this is V and this is U. So the signs may look similar when I am writing it quickly. And here your beta is equal to 1 by V del V del T at P constant. So this del V del T at P constant becomes simply beta times V, right? So from here you can use this, you can replace this term by beta V, and you are getting P plus del U del V T constant into beta times V, right? Now beta value you have already calculated in terms of alpha, that this is 3 alpha. So this is P plus del U del V at T constant 3 alpha V. Now what is del U del V at T constant? This is change in internal energy with respect to a change in volume at constant temperature. Now generally this value is ideally 0. Why 0? Because we assume that internal energy U is fully kinetic. We assume that for ideal gas there is no intermolecular attraction or anything, so there is no potential energy term that is involved here. So U is totally coming from the kinetic energy of the system, and because of that it has no volume dependence. It is not dependent on the volume of the system, because this is not coming from any energy that is related to the internal force of interaction of the molecules. It's just purely kinetic. So in that case it will be independent of volume, and so the derivative with respect to volume will be 0. So this is when you are assuming, which is the general assumption, that it's ideal and no force of intermolecular interaction present. So no potential energy PE. U, the internal energy, is totally kinetic, and hence it will not depend on the volume or whatever in the system, because it is only dependent on temperature, right? So then this is 0. So from here we get this term 0, and we are only getting 3 alpha PV. Now the volume, we do not have information about volume directly in the question, so we have to convert it into the known terms. So volume is basically mass by density. So finally we are obtaining that this is 3 alpha Pm by rho, which is our final answer, Cp minus Cv. So let us go back. What was the correct answer? Yeah, so option number D is matched with our answer, 3 alpha Pm by rho, and this is also the accepted answer. So with this we have solved all the questions. Some practice problem and also the current week's assignment has been fully solved. So hopefully this will be helpful to you. You can cross verify your answers, and you can cross check your solutions as well from here. So we'll meet in the next class.